This lecture on the radiation balance is based on Chapter 3, the radiation balance, in the book by Villalobos and Ferreres, Principles of Agronomy for Sustainable Agriculture. On the top of the atmosphere, we receive a total radiation normal to the sun rays close to 1400 watts per square meter. This is called the solar constant. This short-wave radiation coming from the sun is composed of ultraviolet. We can see in the spectral irradiance curve shown here, we see the ultraviolet below 300, the visible between 400 and 700 nanometers, and the near infrared that goes from 700 to 3000 nanometers. The amount of energy reaching the Earth's surface is shown also here, and the difference is that the amount of radiation absorbed, the yellow area, is the amount of radiation absorbed by different atmospheric components, basically water vapor, carbon dioxide, ozone, and other greenhouse gases. The amount of energy reaching the top of the atmosphere is composed of 5% ultraviolet, 43% of visible or PAR, and 52% of near infrared. The long-wave radiation is governed by the law of Steffan-Bolztman that states that the amount of energy emitted by any body in nature is proportional to the fourth power of its absolute temperature. And here the coefficients are: first, emissivity, which is the effectiveness of the body in the emission of radiation, and emissivity is by definition 1 in the so-called black body, but in nature, when we think about green leaves or crops, the emissivity is fairly close to 1, close to 97 to 99 of 0.97 to 0.99 of emissivity. Sigma is the Steffan-Bolztman constant, and T is the absolute temperature of the surface emitting radiation. This equation can be used to deduce the temperature of any object by measuring the emitted energy in the far infrared spectrum. The variations of radiation throughout the day or during the year are associated to changes in the solar angle. Here in this picture we see the direction of the sun rays, and we characterize the sun inclination by its zenith angle, which is the angle between the sun rays and the vertical over the surface. If we want to calculate the flux of energy on a horizontal plane like here as a function of incoming radiation in the direction of the sun rays, the relationship is like this. It's the so-called cosine law, where I, the flux of energy on the horizontal plane, is equal to IP, that normal to the sun rays, multiplied by the cosine of the zenith angle. And the cosine of the zenith angle can be calculated using this equation, where we have a function of lambda sub s, which is the latitude, delta sub s, which is the solar declination, and h sub a, which is the solar angle, that changes throughout the 24-hour period, being 0 at solar noon. The solar declination represents or is responsible for the seasonality in the Earth. Here we see the conditions of summer in the northern hemisphere, where the sun is, where at that time we have a solar declination of 23.45 degrees, and the sun is more normal to the northern hemisphere. The opposite occurs during winter, when the declination is minus 23.45, and we have the sun more normal to the southern hemisphere. The value of solar declination might be calculated using this equation, where d is solar declination and we have a function of the day of the year, going from 1 to January the 1st to 365 for December 31st. When the radiation reaches the top of the atmosphere, now it has to go through the atmosphere. There it will be subject to different atmospheric processes. The first of all is absorption, which is due to molecules like ozone, water vapor, CO2, or oxygen. Apart from that, we have a scattering of radiation that is due to molecules, but also to particles and aerosols. In the visible band, scattering is much more important than absorption, and infrared, and for infrared, absorption is more important than scattering. Those processes generate a so-called diffuse component of solar radiation. Diffuse in the sense that it comes from all the hemisphere, it comes from all the sky. On the other hand, we have a component, radiation of the beam, or direct radiation, that will come with the direction of the sun rays. The sum of those, of direct and diffuse radiation, is the so-called solar or global radiation. The component of solar radiation in the PAR, in the visible bands, is 45% of solar radiation at the Earth's surface. The PAR, photosynthetically active radiation, is the fraction of shortwave radiation that can be absorbed by chlorophylls. It also is basically also equal to the radiation bands that can be detected by the human eye, and that's why it's also called visible. The fraction of diffuse over global radiation depends on the solar angle and on cloudiness. The extreme conditions would be for completely overcast skies or during twilight, before sunrise or after sunset. We have a fraction of diffuse over global close to 1. On the other hand, for clear skies and close to solar noon, the fraction of diffuse over global radiation is only between 10 to 20%. We can measure solar radiation using pyranometers in weather stations like this one shown in the picture. This is a silicon pyranometer, rather cheap sensor. And for many situations we don't have measured values of solar radiation and we need to estimate them. We can estimate solar radiation according to cloudiness using this equation, where solar radiation is a linear function of the fraction of hours clear over total day length multiplied by extraterrestrial radiation. This is the radiation received on the top of the atmosphere. According to this equation, for clear skies, we would have on average around 75% of extraterrestrial radiation. On the other hand, under overcast skies, solar radiation would be only around 25% of extraterrestrial radiation. We have an alternative to using cloudiness, and that is using the daily temperature range. Using this equation, solar radiation is proportional to extraterrestrial radiation multiplied by the square root of the temperature range of the day, the difference between Tmax and Tmin. Here, KRS is a proportionality constant ranging between 0.16 and 0.19. The reason why we can estimate solar radiation in this picture, we see the time course of Earth temperature for 2 consecutive days in January 2017 in Cordoba. First, we have clear sky conditions on the 18th, the black line, like here, and the conditions with clear sky conditions, we have an important decrease in temperature during the night and an important increase temperature during the day. Why? Because the losses of long-wave radiation during the night are lower and the gainings in solar radiation during the day imply a greater heating of the air. On the other hand, when we have cloudy conditions like on the 19th, we have almost no cooling during the night and we have less heating during the day, like here. That is why the variation in temperature is related to atmospheric transmissivity, in other words, to cloudiness, and therefore we can use the temperature range to estimate solar radiation. In those equations, it is important to estimate extraterrestrial radiation, in other words, the amount of radiation in the absence of an atmosphere. Its value will only depend on latitude and time. We can calculate extraterrestrial radiation using this equation, where the R is a correction due to the distance from the Sun to the Earth, and then we have delta sub S is latitude, lambda sub S is latitude, delta sub S is solar declination, and HS is a function of latitude and declination. HS is half the duration of the daytime expressed in degrees. Therefore, the day length is calculated as 2/15 multiplied by HS. dr is also a function of time, so we calculate it as a function of day of the year using this equation. For instance, we will calculate day length and solar radiation for clear days on December 21st, which is day of year 355, at South Hobart, Australia, which is 42.9 degrees to the south. Solar declination and the correction dr depend on the day of the year only. So applying the equation first for solar declination, 23.45 multiplied by the cosine of 360 multiplied by day of year 355 minus 172 divided by 365. That equals minus 23.45. We could already know this because it is December 21st, and at that time solar declination has an extreme value close to minus 23.5. On the other hand, the R is equal to 1 plus this function, where 355 is day of year, and we come up with a value of 1.033. Therefore, now that we know declination and we know the latitude, we can calculate HS as the arc cosine minus tangent of the latitude minus 42.9. Look that for southern locations we considered latitude to be negative, multiplied by the tangent of minus 23.45. Therefore, HS equals 113.8. And day length is calculated as 2 multiplied by HS over 15. In other words, 15.17 hours of day length. Now we apply the equation for extraterrestrial radiation, substituting for the R 1.033, lambda sub S, the latitude, minus 42.9, declination, which is minus 23.45, and HS, which is 113.8. And we arrive to a value of 44.5 megajoules per square meter per day. Finally, we assume that for a clear day, solar radiation is 75% of extraterrestrial radiation, and we come up with a value of 33.4 megajoules per square meter per day. In this graph, we only emphasize the idea that for the same latitude, the radiation will be greater for an arid location than for a wet location. Here we have the potential radiation for this latitude, where we have two different locations, which is Pelotas in Brazil, which is a wet location with a rainfall above 1,000 millimeters per year, and we have Claver, which is the discontinuous line, where we have only 174 millimeters per year of rainfall. Here we show the idea of the amplitude in the solar radiation curve throughout the year. We have three locations: Bosaso, Somalia, 11 degrees north; Sharjah in the United Arab Emirates, 25 degrees north; and Las Vegas, USA, 36 degrees north. As we move away from the equator, this would be Bosaso, close to the equator; this would be Sharjah, and this would be Las Vegas. As we move away from the equator, as we increase the latitude, the amplitude of these curves increases. So we have greater seasonality as we move away from the equator. In this graph, we see the variation of mean annual solar radiation for different locations of the Earth as a function of latitude. We see that maximum values of solar radiation are attained from minus 30 to plus 30 degrees of latitude. There is typically lower radiation values close to the equator due to higher rainfall, but in general there is a variation in parallel to the potential radiation for the different locations. Part of the radiation reaching the Earth is reflected by the crops, the soils, etc. The reflection coefficient for shortwave radiation is the so-called albedo, and it affects the radiation from 300 to 4000 nanometers. In other words, what is shortwave radiation? In this photograph, we show how, for a light-colored soil, the albedo of the soil depends on its wetness. We see that the dry soil has a much lighter appearance than the wetted soil, which looks darker. Albedo reflects the greater the albedo, the clearer we will see the colors. In this table, we see values of albedo that only for fresh snow are close to 1, but for other surfaces would go from 5 to 35%. For dry sand, for instance, or dry light soils would be 35% of albedo. Dark soils would be close to 0.1 of albedo, and water bodies also around 10%. Annual crops would range from 16 to 26%, and orchards would have lower albedos than annual crops and would range from 5% of coniferous forests to close to 20% for some deciduous forests. Apart from the losses due to reflection of radiation from the Earth's surface, we will have losses due to thermal radiation. Thermal radiation or long-wave radiation will affect or will include the radiation emitted by the crop. That would be radiation going upwards. Then we would have part of this radiation is absorbed by the atmosphere molecules, mostly water vapor and CO2, and then the atmosphere will emit radiation according to its temperature and to the concentration of these molecules, and part of this emitted radiation will go back to the Earth's surface. In general, the balance for thermal radiation implies long-wave radiation losses. And we can calculate these losses as a function of the cloudiness, the vapor pressure, and the air temperature using this equation. If we know the long wave losses and we know the albedo and the solar radiation, we can calculate the net balance of radiation on the surface, which will be equal to 1 minus albedo multiplied by solar radiation minus the losses of long wave radiation. For instance, previously we calculated that under clear sky conditions on South Hobart we have a solar radiation of 33.4 megajoules per square meter per day. Let us calculate that would apply to December 21st. Let us calculate the net radiation over short grass, which has an albedo of 0.23, if the average air temperature is 25 degrees, and the air vapor pressure is 1.8 kilopascal. First, we calculate long wave loss, and we apply this equation RB. First, we have the component of cloudiness, and here we have the ratio of hours with sunshine over total day length. As it is complete clear sky conditions, this ratio is equal to 1. Then here we have the vapor pressure, and here we have the mean temperature. We come up with a value of 5.88 megajoules per square meter per day. That is the loss of long wave radiation. Now we apply the equation for net radiation, 1 minus 0.23 multiplied by solar radiation, which we had already calculated, 33.4, minus 5.88 megajoules. And we arrive to a value of 19.8 megajoules per square meter per day. In this picture is only to show how different the thermal images look. For instance, when we see a tree and we see the sky above, looks much colder than the tree. This tree is close to 0 degrees, and the sky would be around 20 degrees below. In this other picture, we see an olive orchard where we have an area here that shows some water stress, and therefore the temperature is warmer than the rest of the orchard. We see also some isolated trees like here, or in this edge where watering was probably worse, so the temperature was warmer. In this graph, we show the time course of the different components of solar radiation, net radiation, reflected solar radiation, and long wave losses over a cotton crop in Cordoba in the summer of 2003. We have typically curves of solar radiation like cosine curves with maximum during solar noon. We have a value of 0 during the night for solar radiation, and then we have the reflected radiation would be this one, which is in proportion to incoming solar radiation. Then we have the component of long wave, and this is the long wave losses. If you see, the component of long wave loss is close to 100 watts per square meter. And now, if we calculate the net radiation, we come up with this curve. Look at this. During the night, we have negative values of net radiation, and during the day, we have positive values in proportion to solar radiation. Once we have an amount of radiation reaching the top of the canopy will absorb part of this radiation. If we call the incoming radiation I sub 0 and we call the radiation at the solar surface I, we can calculate the radiation at the solar surface using this equation, where I sub 0 is incoming radiation and multiplied by an exponential function of a parameter k, the extinction coefficient, times the leaf area index. The leaf area index is the area of leaves per unit area of ground, and the extinction coefficient is a parameter that reflects the capacity of the canopy to intercept light. The difference between incoming radiation and solar radiation at the solar surface is the so-called intercepted radiation, I sub 0 minus I, would be equal to I sub 0, 1 minus the exponential function. The extinction coefficient is a parameter that depends mostly on leaf inclination. Here we plot values of extinction coefficient versus the parameter of leaf inclination, where 0 corresponds to vertical leaves and values above 5 correspond to horizontal leaves. We see that the extinction coefficient for vertical leaves is close to 0.4, while for vertical leaves is close to 1. In this table, we see values of the extinction coefficient and the inclination parameter for different crops. Extreme values would be for sunflower 0.9, which has rather horizontal leaves, legumes 0.809 have also high values, while for cereals we have values close to 0.405. For summer cereals like maize, sorghum or millet, we have 0.607, etc.